Hi, everyone, and welcome to today's discussion. So today we'll be doing one of the posters that I saw at NeurIPS that was very black and very big, very eye-catchy. So this poster was on deep differentiable logic gate networks. So what exactly is this? So it's basically, instead of using neurons for a neural network, where the neurons have their own weights and biases, we use logic gates. So it's a very simple idea, but it manages to run much faster than neural networks. And also it manages to achieve like similar accuracies to a neural network. So this has potential to run in perhaps edge devices. Okay, but the reason why I wanted to present on this is not actually the fast inference time, because actually it takes about 3 to 4 times longer training time as compared to a neural network. Why I'm interested in this is because it kind of simulates a neuron in the brain more exactly than the current neural networks, because the output is kept to a magnitude of 1, because logic gates you only can go up to 1, 0 or 1. Yeah, so I'm quite curious to see whether we can model architectures in the current neural network using neurons that more closely resemble like what the brain's neurons do. Like you have a magnitude cap, and then basically based on that kind of limitations, you can actually avoid problems such as gradient vanishing or gradient exploding, the kind of problems that recurrent neural networks faces. Because you kept the output, you can avoid those kind of problems. So I'm interested in this more for that reason. Okay, so let's take a look at what exactly is a logic gate. All right, and sorry, first we start with a perceptron. All right, so I took these slides from my professor, Prof. Mehu. So this is basically how a perceptron looks like. I'm sure most of you already know, but let me just describe roughly. So like this is inspired loosely from the neuron. So you have like your input from the different input neurons here. Okay, maybe I shouldn't use red. Let me use another color. So you have your inputs from your other cells, and these inputs here, okay, it's not drawing. The inputs over here will be given through the dendrites. Okay, and after that, if of a sufficient potential, this will spike an action potential that will go through the myelin sheath. Okay, if there's a sheath, or basically it just goes through all the way to the axon, and then it goes to another cell. So this is like how a neuron passes a message down. So in neural networks, we simulate this by using different like input weights from the different like input like branches that simulates a dendrite. Here, the weight is very similar to like how receptive these dendrites are to neurotransmitters. Like for example, increase in NMDA receptors. Yeah, so these weights here can be either like potentiated or depressed, like long-term potentiation or long-term depression. And you adjust these weights according to like, it's a proxy to maybe like how much receptors the cell has. So there's some biological relation to this, although we made it into a math thing after a while. So this is how a biological neuron is. Okay, then we go through some form of summation to sum up the inputs. And then there's an activation function that determines whether or not it spikes. So this is the neurological basis of how a neuron was initially created. And you can see that this is like the equation for a perceptron, okay, a single neuron, right? So you sum up the input weights, and then you have an activation function here. Okay, over here, this is like a step function, or it can be other activation functions. So this has been quite successful. Now the deep learning is all entirely based on this kind of perceptrons. Okay. Then now we go to logic gates. So logic gates are actually based on like the computers. Like in electrical engineering, we always like to talk about like using logic gates, like FPGA boards, circuit boards. You can actually program certain logics using logic gates. And there's actually quite a lot of formulas that say that, oh, any kind of logical expression can be all expressed as NOT and AND gates, if I get it correctly. I think it's De Morgan's law. Yeah, I can't remember exactly it. So Dylan is correct, right? De Morgan's law, right?
All I remember is that you can convert from the NAN and the N through this De Morgan's law.
Yeah, NAN and something, NAN and N.
No, I remember NAN and OR. Yeah, right.
NAN and OR. Yeah, so with this, you can modify, you can model any kind of logical relation between the input and output.
So what is the name of the law? It sounds really interesting. So is it
De
like
Morgan's law.
the
Yeah, basically you
Morgan's
can
law?
express anything as a, if I remember correctly, it's a NAND gate or NAND and OR gates. Yeah, you can basically represent anything using those two. Yeah, so this basically it's a way to say that there's some form of universal expressivity in logic gates as well. Yeah, and this is like something like the universal approximation theorem for a single neuron. Yeah, so this happens when you can do like logic gates in layers. Okay, much like for universal approximation theorem, you kind of need like, this is your input neuron. You need your input neuron to go through to your hidden layer and then your output layer. So this is universal approximation theorem for neural networks that says that it can model any function. Okay, continuous or non-continuous. This De Morgan's law, you can actually model any logical relation. Like logical relation as in you have certain inputs and then you can just do like and or not. Yeah. So there's some power in logic gates because actually our
Wait, but
computers are powered by logic gates as well. Oh, sorry, who's speaking?
it's like in the Wikipedia link, De Morgan's law is a set of transformation rule. But what we are referring to here is like the kind of law that describes you can like the thing that relates a set of and or operation to approximate any type of functions or binary functions.
I think yes, only binary functions actually. It's not any kind of function because the output is always either 0 or 1 for logic gates. Yeah.
So the basis of what Chomin was saying is that let's say you have a certain logic you need to satisfy. So like for example, some A and B logic. So what Chomin was saying here about De Morgan's law is that let's say you are only allowed to use NAND and OR gates. You don't have access to AND or you don't have access to nor the XOR gate. If you're familiar with this respective logic, you can actually transform the logic to fit the requirement that you only allowed to use NAND and OR gates via this De Morgan law, you see.
No, so in the end,
Okay.
what the logic will look like is probably like that AB plus AC. Yeah, I mean, there's a way to transform like multiplication into addition using De Morgan's law. So
Yeah.
ultimately what will happen is you have a sum of products. Yeah, and then you can just model each of them by a logic gate. And this plus is the OR. This is like the AND. Yeah, so in the end, you have a series of relations like that. Yeah, so this kind of logic gate expression is actually what they use in the FPGA chip programming, few programmable gate arrays. Yeah, so this actually has been quite long-standing in electrical engineering, and it shows that logic gates can actually express quite a lot of relations, but as what Shusheng said, is mainly limited to binary relations because the output is limited to 0 or 1. Yeah, so yeah, that's the thing about logic gates. That's why logic gates are quite expressive in that sense. If you only want binary outputs, you can actually express quite a lot of relations. So let us just look at this logic gates here. So this is like an AND. And basically if the inputs A and B are positive, like 1, then the output is 1. Inclusive OR, this one you can see that either one is positive, then output is positive. Okay, this is OR. Okay, exclusive OR is basically when only the 2 bits are of different parity, 0 and 1 or 1 and 0, then output is 1. Okay, so this is how it looks like. And okay, as a quick exercise, all right, this is basically like a neural network over here. A neural network can also be said to be modeling a logic gate. Okay, so this one again from my prof's slides. So you can see that this perceptron is actually a linear separator because why? This is actually the equation of a linear line. All right, and then you just apply a threshold function to your linear line. Hence, the kind of classes it can separate is like you draw a line on your input space, and then basically this one all become like class 0, and this one all become class 1. To the left of the line is class 0, to the right of the line is class 1. So it can function as a linear separator. So there's some relation between neurons and logic gates in this kind of sense. All right, so let's go to the very typical kind of problem. I don't know if you all have heard of this before. So let's look at like logic gate functions and see which one can be separated by a straight line. All right, so n can be separated by a straight line over here. You want to chip in, or can all be separated by a straight line? The classes. Okay, let me just answer. All right, it can. All right, so now the question is, can XOR be separated? The classes, can XOR be separated by a straight line?
Not conventionally.
Yeah, so you see, you can't really separate this by a straight line like that. Okay, because like no matter how you distribute your classes, like there will be like at least one of them that is incorrectly classified. So this is actually the problem with perceptrons. And if you all know this person called Marvin Minsky, he wrote a book called Perceptrons. And he argued that a perceptron cannot model an XOR logic gate. And that was the start, as in what the history books say, that was the start of the AI winter, because people say that, oh, look, neural networks cannot model everything. So it's not very good. Okay, but, okay, although it cannot model this kind of like non-linear relation, what was later found is that multi-layer perceptrons can. All right, so multi-layer perceptrons, you can treat it as like this. You first separate it by maybe like by one perceptron like that. So this one, I call it, maybe I call this class 1. And then all this will be like class 0, 0, 0. Right, so this is one separation. Then maybe you separate by another. So this can be like an AND gate or OR gate, okay? Because this one, okay, maybe we just use the logic of the OR gate, okay? Because OR gate is, okay, let me just erase this. Okay, so it's easier to see. So maybe the first gate that you see here, this one, maybe you use the logic of the OR gate. So this is 0, and then this one will be 1, 1, 1. Okay, and then what we'll do next is we'll use maybe an AND gate. So what we can see in the AND gate is that the top here, actually what I want to do is I want to use another OR gate. It's just that the OR gate is kind of in a different way. So over here, this is class 1, and down here is class 0. So we can see this will be like that, like that. Okay, I think I mess up the representation. Let me just erase this. Yeah, I want to show that if you can use 2 layers, you can actually represent the XOR function. So this one has to be like, let me think about it. This one has to be 1. Oops. This is 1. This is 1, and everything else here is 0, 0, 0, 0. And then similarly for the red line there, it's 1 on this side, and everywhere else is 0, 0, 0. Okay, so now we have mapped our input representation into like 2 separate kind of features, all right, based on 2 linear separators. All right, how can we then get the XOR function using this? Okay, so you notice that 1, 0 is this black one, and over here this is 0, 1. Right here 0, 0, 0, 0. So maybe you could use like some form of feature separator that, okay, so I realized that I made a mistake here again. So let's replace all these zeros with 1, all right? So this should be 1, 1, 1, 1. Okay, basically I want to do an AND gate at the end. And let me just redraw this again. All right, let me just redraw this again. So this one should be 1, 1, 1, 1. And then this one will be like 0, 1. And then this one will be 1, 0. Okay, so the only case whereby both linear classifiers classify both as 1 is at this middle nodes here. And then later you can just do an AND gate in order to like say which are the classes that should be classified as 1, which is this middle class over here. Because this 2 here will be classified as 1. This one will be classified as 0. If you use an AND gate, this one will be classified as 1, and this one will be classified as 0. So you can see a combination of maybe like an OR gate and an AND gate can lead to the XOR kind of gate. So you can use a multi-layer neurons in order to model an XOR gate. So yeah, this is how I how we link a neuron to the logic gates. So as what I described earlier, like a multi-layer perceptron can model all the logic gates. Okay, because you can, although the decision boundary may be non-linear, you can stack multiple linear decisions, and then in a new kind of input space. So like over here, what you can do is you can actually map the input space. So like initially the input space is like that. Initially the input space is maybe like X, O, X. Okay, after we do two linear separators, maybe the input space will then be mapped into something like this. It'll be mapped into like this. Like maybe the O's will be one side and the X will be one side. Then you can then use another linear separator, which is like a perceptron, and then you can separate the classes again. So an MLP can model that kind of logic gates, right? So you can see that if we use like something like a logic gate, we can actually model this kind of relation much more easily than a neuron itself. So there's some benefits with logic gates. So let's think about like what are the differences between neurons and logic gates. So one thing, okay, this is taught by me, okay, this is not in the paper, right? So a neural network, a neuron can actually specialize into a logic gate because it can perform that kind of function if the line is matching exactly what the line is for the logic gate. Okay, however, for this kind of logic gate, in order to express fully this kind of relation, because you can see over here, these are arbitrary weights and biases. Over here, this is actually fixed weight and bias. Okay, your logic gate doesn't change its function, you see. So in order to model an arbitrary kind of like relation between input and output, plus this kind of non-linearity, you kind of need a lot of this kind of logic gates in order to emulate this neuron. So there's some downside to it. You cannot model binary output relations that easily compared to using a neural network, a neuron. So what are the kind of things that are different as well? So you can see over here that what I put here, perceptron, at least for the neuron itself, okay, one single neuron can only model a linear decision boundary, right? Because of the way this perceptron is structured. Okay, even if you use an activation function, because it's still a thresholding kind of function, you still have to do a linear decision boundary between your classes. Okay, a logic gate, however, can actually model non-linear boundaries like XOR. So logic gate is actually kind of superior here, right? It can be more expressive. Just one logic gate will be sufficient to do what we did with like a multi-layer perceptron. Okay, the good thing about neurons here is that it can learn a function pretty flexibly, like because you can actually do back propagation and you can learn all these weights here. Okay, but this guy here, this logic gate, you cannot learn the function. The function is fixed. Okay, so this paper actually used a way to bypass this later. We'll go and dissect how this paper does it. Quite interesting. Yeah. So the last one is neural networks actually are very, very slow to learn. All right. If you ever played with neural networks before, it takes a few epochs. Like for MNIST, maybe 3 or 4 epochs of the entire data set of like 50,000 images to actually learn the classification. Okay. However, if you know the right combination of logic gates, you can just run it immediately and you learn. Okay, but this is actually playing cheat a bit because you still need to train the network to actually find out what are the best logic gates to use for the network. So that actually takes a while. Okay, any other points to add to this?
I think it's not that accurate. Why do you say the multi-layer perceptron only models linear decision boundaries?
Oh, it's not a multi-layer perceptron. It's a perceptron, only models linear.
Or single, is it perceptron?
Yes, because you are comparing apples to apples. Is it one neuron to one logic gate? Yeah, but of course, if you use multi-layer perceptron, you can model non-linear decision boundaries. Yeah. So actually, for some use cases, you just need logic gates. All right. If let's say your function is it can be those kind of binary functions where your output is 0 or 1, like a 0-1 classification problem, you can use logic gates and it will run much faster. Yeah, in fact, people have done like for binarized MNIST where the output is either 0 or 1. That means like the digits 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, yeah, it's class 0. And then 5, 6, 7, 8, 9 is class 1. So actually using the logic gate networks is actually much faster and also much more accurate than using neurons. So there's some benefits to using logic gates in that sense. All right, you want to add any more things to this before I move on to the next part? Yeah, it's quite interesting actually, this idea of using logic gates. Right, so then we ask ourselves this question: if we want to do a logic gate network, what kind of logic gate should we model? All right, so in this paper, what they did is they actually have two different inputs, A and B. Let's call them A and B. And then this logic will then be every single combination of A and B. Like if my A and B are 0, 0, A and B is 0, 1, A and B are 1, 0, A and B are 1, 1. So if you know, like, let's say each of these has two possible outcomes, the total number of logic gates that are possible using like a 2-input logic gate is actually 2 times 2 times 2 times 2. There's a total of 16 logic gates. And in this paper, I was quite surprised they actually model everything. Yeah, because earlier on we talked about De Morgan's law. Actually, if they like model the NAND gate, and the NAND gate is like the not A and B. This is the NAND gate. You just model the NAND gate, and then you sorry, NAND gate is not this. This is the NOR gate. All right, the NAND gate is, I think this is the NAND gate. Yeah, so if you just model the NAND gate and OR gate, okay, I might be wrong here. Yeah, to go and check again. If you just model these two gates, actually you have universal modeling capabilities already. So there's actually some question like some of the reviewers also ask like, why do you want to model everything? And it turns out actually they say that if you don't model everything, the performance is worse. Okay, so this is my theory. All right, I haven't tested out on their code. My theory is that this is important because in the logic gate networks, there's no way to shut down the logic gate. So you need to like replace it with like a 0 logic gate in order to shut down the logic gate. So that's a drawback of the system that they implemented. I can think of a way to implement it better, their logic gate network, so that you can actually just use 2 gates and then you can conquer the world with those 2 gates. Yeah. So in this paper, they use all 16 logic gates. Okay, but I think there's a way to do it better. Okay, let's move on. Oh yeah, sorry. One last thing to say. Instead of just using like A, B to Y arbitrarily, there's also a way to actually model it as a relation. Okay, so here you can see it's A times B. So actually it fulfills the same role as the logic gate output. Okay, so it's only A and B are 1, then this will be 1. If either one is 0, then it'll be 0. Okay, anyone want to guess why they did this kind of equation here? Like what would be the benefit of doing this if we were to do like if we were to do backpropagation? You want to guess? Like why did they bother to come up with an equation for each of this?
Differentiable.
Yeah, correct. It's differentiable. So this is one of the key ideas behind this differentiable logic gates, is that they actually map the function between the inputs and outputs in a differentiable equation. Here they use multiplication, but there's many other ways that you can map this kind of inputs to this kind of outputs. There are other kind of functions as well, but here they mainly work on this kind of multiplicative probability kind of approach. All right, next slide. So how do they do this kind of so I mainly focus on the classification results because I think their regression is a little arbitrary. Like they put in some scaling function that is like hyperparameter tune, which I think is a bit not very ideal because you still need to go and tune it yourself. So we just talk about the classification case because it looks more natural to me. So the classification case, what they do is they take the image. Okay, so this is like a sci-fi image, maybe of a panda. Okay, what they do is they split into different cells, and then each cell they have different colors channel, like red, green, blue, right? Then each of these channels, okay, what they do is they do a thresholding, and then the input to the gate can only be 0 or 1, so they just threshold like above a certain threshold is 1, if not it's 0. Then they do like different channels, and then they come out with grids of 0 and 1 for the colors. So it's actually quite how you will lose a lot of information here, but surprisingly you can still classify. Like MNIST you can definitely classify, because MNIST you actually don't need the color information, you just need to know where has ink and where doesn't have ink. Sci-Fi they did a little poorly because of, I suspect it's because of this way of discretizing the input into zeros and ones. Right?
Yeah,
so
not only that, for sci-fi it's more natural images. You do this right, you lose the bias of what we call spatial bias, where you select a certain pixel, you can tell what's the neighboring pixels.
Correct. So this is definitely not ideal. You need a CNN kind of architecture for images, ideally. And this logic gate networks haven't reached that stage yet. But it's interesting based on its current state of like, you're just arbitrarily assigning ones and zeros based on some threshold of the different color channels. Okay, then you just linearize them because there's no way to model like patches in this network yet. So you just linearize them. Okay, then this is the crux. Okay, I can just describe the training right now with this. They actually randomly connect the input by some random seed to like different gates. So these gates, each of them can only take in 2 inputs. So they just use the random seeding in order to basically put the inputs into like the logic gates. Okay, Jet says convolutional logic gate networks. Yeah. I mean, if you can just repeat, because like convolution is shared weights, right? I'm sure you can do shared logic gates. So you just need to change the architecture to fit it. I think it can be done. Yeah. So if you want to do this, but the thing is you already lose information at this level by discretizing 0 and 1, unless you binarize it. So like if your pixel is 256, like, if you have 256 different colors, that's actually 2 to the power of 8. So you can actually do a row of 8 bits, like maybe like this 0, 0, 1, 0, 1, 1, 0, 0. So actually, if you can binarize your input bits like that, maybe you lose less information and then it will be better. Yeah, but then again, it will be like the network needs to figure out that this comes from the, the network will need to figure out that this comes from the same like information. So this is definitely doable if you use like binary inputs and not lose information. So that's possible. Okay, so the first part of the network is basically randomly connect the connections into the different logic gates. Right, and then we do that for every single layer. So we also randomly connect here and randomly connect here. Okay, and here comes the drawback of their network. These connections are fixed. Okay, and not just fixed. You basically cannot change the connections at all during the training or testing. And there's no way to like shut off the connection as well. So if let's say you realize that you don't want to like connect here already, like this one you want to make it an output of 0, there's no way to shut off the logic gate here. Okay, so what they actually implemented is they implemented trainable logic gates. Basically, this logic gate here can be modified. So you see this, whatever I drew in purple, so I'll actually draw for all of them. All of this actually, there's a probability function to actually state which logic gate is the most preferred. Okay, later I will cover more of that in the next slide. But all these are actually learnable. So you can actually choose your logic gates through learning. So you can choose the right logic gates through learning. So that's why I suspect the architecture having the gate as a 0 gate, which means that no output, is actually very important, because sometimes you want to shut off the wrong logic gates. Like a wrong weight you want to tune down to 0. Currently, you cannot tune the weights at all because there's no weights in the logic gate network. The inputs, there's no like way to tune the weight. So actually one thing that could be done is, I'm not sure if you all have heard of this architecture called GALU, gated ReLU. So what gated ReLU does is that you actually multiply the output of your ReLU, okay, by basically the input itself, pass through some MLP. Okay, so if you all heard of this thing called GALU, gated ReLU, you actually multiply the output by a gated term between 0 and 1. Yeah, so you actually use the neuron itself to tell you like whether or not, okay, this is a turn out bad. Okay, you actually use the neuron's inputs itself to tell you how much of a volume knob to actually tune the neuron. So I guess if they do something like this over here, where you can learn by backpropagation how to tune this volume knob for your gate, actually, you may not need to switch the gate during training. You can just start with the same gate, end with the same gate, and then you just tune this volume knob, right? Because later, if you see in what I described, most of the training time actually comes into choosing what this logic gate should be. So they actually lost quite a lot of training time there. Like a lot of training time was spent just to configure the right gate, because every time you change the gate immediately, right, you actually change the entire network function altogether. It's a very sudden shift. Unlike neural networks, when you change your weights by gradient descent, actually it's a very gentle shift to the local optima. Here, when you change the logic gate, it's a very drastic and sudden shift to the entire loss function. So this is one of the reasons why the training is like very, very swingy. Yeah, it takes quite a while to converge. And I guess if they do something like this volume control here, where you use the input, pass through some, okay, over here, unfortunately, you may still need to use some form of like a sigmoid function here, a sigmoid function with like Wx plus B. Yeah, so you have to use some form of neurons here in order to do this kind of volume control, but I think it will actually help the network quite a lot. Okay, I haven't tested this out, but this is just my theory. Okay, any questions so far on this? Oh yeah, I forgot to talk on the last part, which is how to classify. So what they do is actually they just take the sum of these ones here, and then the majority wins. The majority of the ones win. So if let's say here giant panda is given a score of 2, and here red panda is given a score of 0. So the class is called giant panda. Right? Of course, to train this is a little tricky because you cannot just do like summation like that, and then there's no way to do a loss function by just counting. So when they train, they actually use a softmax, okay, and then they differentiate via the softmax. So I'll talk more about that later. But based on this diagram so far, any questions on like how the logic gate networks is created?
Did the author suggest why they use random shuffling rather than in-place pairing for to fit into the logic gates?
Say again, what do you mean by in-place pairing?
So we are going to process the picture of the panda into some long binary string, right?
Yes.
And you say that the author, instead of doing, so when I say in-place pairing, let's say there is a 0, 0, 1, 0. How logically what you would do is like you just feed like pairwise. So 0, 0, and then 1, 0, and then 1, 1, 0, 0. But according to what you were presenting on, the author actually shuffled this, right? Shuffled the binary string.
I mean, in some sense, you can consider that as shuffling because the connections over here are shuffled. Like these connections here are all like there's no relation to the input at all. It's just like by random seed, you just map the input to logic gate. Yes. So in that case, you can also treat it as a shuffling of the
did the author like suggest why they do that?
Well, because a logic gate that they use only can accept 2 inputs, and you know, unlike an MLP where you can connect to everything the previous layer, is forced to be sparse. I mean, it can be a good thing actually. Yeah, but because of that, they actually lose out on like certain expressibility. Because if you connect wrongly in the beginning, you may not get the right relation anymore. Yeah, so it's very unlike like network pruning where you start with a very dense network and you prune out unnecessary connections. Here, your starting connection actually determines how well the network learns. So how the authors mitigate it, they have 10,000 over neurons per layer or 10,000 over logic gates per layer to try to mitigate this issue of maybe starting with the wrong connections. But this is unscalable because like if you go deeper and deeper, you just cannot cater for all the right connections to be done in the right place to begin with.
I see. I guess it's because they want to try to emulate convolution network in a way, but they are not able to do that. So if they were to do like in-place pairing, you only have those connections in the neighbor, then you may not be able to gain any information regarding, let's say, the first pixel relation to the, let's say, the second last pixel relation. But then it's also very dangerous though, like, because it's all based on random seed, right?
Yes, correct. So different random seed will have different performances. But just like a neural network also, you start with different weights based on the normal distribution.
No, but at least a neural network, even though your search space is much larger, but then you're at least like guaranteed that the solution is within that boundary. But in here, it may or may not be. Or even if you can guarantee to some extent, the optimum or the local optimum you're looking for is not really that great.
Yeah, that's why when they did this logic gate changing thing, which you will see in a bit, I was kind of opposed to it, because when you change the logic gate, your loss function would, imagine your original loss function was like that. The moment you change the logic gate, your loss function might become like that. So it's very difficult to actually learn if your loss landscape suddenly changes so drastically. Because when you change the logic gate, you change the function drastically. From like a dot b, maybe you can change it to another logic gate where it's like not a dot b, which is like a total 360 degrees change of the output. So yeah, this is the part I disagree with actually. The fact that your logic gates can be swapped by the distribution. They call it the categorical distribution. Yeah. Maybe we talk about the rest first, then we can discuss more on the architecture after this. Let me just present the full architecture first. So for the authors, they actually say that actually there's some inherent difficulty using logic gates for training. Okay, the first difficulty is that inherently the logic gates are not differentiable. So this is a problem that they actually solve in this paper. Okay, the other thing is the logic gate itself, you cannot really learn like what logic gate to put, okay, traditionally. Okay, there are some papers that use evolutionary means like genetic algorithms to actually choose the best possible fit of the logic gates. But you know, genetic algorithms or evolutionary algorithms, when it goes to like 10,000 different gates to choose or 20,000 different gates to choose, it can take quite long to converge. So this is actually not very scalable. Like if you can do something like gradient descent, that will be much, much more scalable to learn like what kind of logic gates to use. So the authors did two things. One is to link inputs and outputs using a differentiable function, which we saw just now. Okay, by mapping like a dot a times b in a like probabilistic way, you can actually do the logic gate functions as well for like the AND gate. And then the second thing is they use another kind of probability method to select the logic gates. So let's see how these two methods work. So the first method is the way that they do the relation. Like for example, the NAND gate is given like 1, okay, minus a dot b, a times b. So a times b, this is the AND gate. So if you do the 1 minus the result from the AND gate, this thing combined together, this will become the NAND gate. Okay, and not just that, in order to make the network a little more expressive, like not just have like 0 and 1 outputs, the inputs itself over here can actually be a decimal place. All right, so you can actually use decimal place here between 0 and 1, and then your output also is between 0 and 1. So this is the advantage of using this kind of functions. You can not just model like inputs that are kind of scaled to 0 and 1. Your inputs can actually be this kind of decimals. So this is one kind of advantage that they did. They relaxed the normal logic gates so they can model inputs that are more like fraction based. So yeah, this is one of the things that they did. Okay, the second thing that they did is they made the gate selectable using backpropagation. And how this is done is like this. You assign each of the 16 gates here some probability that sums up to 1. Okay, how to ensure that the probability sums up to 1? We use a softmax function like this. So this e to the power of wi, which weight wi is like the weight for that particular gate. So the higher this wi, the higher the probability. Like over here, this is definitely like a very high. I think this is a NOR gate. Yeah, so or is it inclusive or? Okay, I can't really see properly, but this is one of the gates that is like 100%, you should choose this. Okay, so if your wi is so high, by softmax, the chance of you choosing this is 100%. So of course, if you want to do a softmax like that, you know, you can actually do like some sort of like quantum superposition of your gates. Like you can have like this gate being activated 20% strength and the other gate 20% and then the other gate 60%. So you can do like an ensemble summation of the inputs. Okay, that is possible. Okay, but the authors didn't do that. What the authors did is they backprop this categorical distribution. So they can learn based on this function of each of these gates, which gate is more important. Learn through backprop. Which gate is more important? Or which gate models the relation better? Okay. And what they actually did is they then, during inference time, select the gate with the highest probability. So it's deterministic in that sense. You don't actually have like a superposition of gates probabilistically in some weighted sum. You actually just choose the gate that has the highest probability. Yeah, so you said might as well use quantum way of what I think actually if they do like the superposition thing, maybe you can have more expressive networks, definitely. But they didn't do that. The main reason is because their key aim is to make it work on edge devices. So in order to make this work on edge devices, if you do this kind of different percentage of like 20% NAND gate, 80% OR gate, that kind of combination, it's very hard to translate that on like an edge machine. Okay, so if you can do this, so the training is basically to choose what is the correct logic gate to use. Then once you select the correct logic gate, you can just put the whole logic gate on maybe an FPGA array. And then you can just run it very fast, very quickly on edge devices. So that's their aim. That's why they didn't do that. But of course, if you do this on a computer, maybe it might be better to just do a probabilistic addition of all the gates together. Yeah, so that could be done. Yeah. So this is how the gate is trained. So using the function itself, C by backprop, which is the more relevant one, then we'll adjust these weights here accordingly. Okay, so this actually leads to very, that's why I say very bouncy training, because when the gate switches, the input-output relation is altered very drastically. It's not a very gentle alteration, unlike neural networks. It's a very drastic one. So this is definitely one of the problems with this network. I was thinking if you make this constant, and then you have some form of tunable volume control here, this might actually perform better. So you just maybe take some function of here and you use this to tune like whether or not to increase the volume or not. Yeah, that actually might be better. And then you keep this fixed. Okay, so this is my suggestion. Yeah, I haven't tried it out, but this is something similar to what I said earlier about GALU, gated ReLU. Yeah, GALU. Yeah. So I think this might work better. But the issue of using this is then you cannot use this on edge devices that easily anymore, because you can't just put them on the FPGA array, because this one probably need to model it using neurons. Yeah. So we said, jokes aside, if I recall correctly, the quantum side is still at the trial and error phase of figuring out the counterpart of classical NN. Yeah, I mean, if you want to use quantum like bits to do like your weights and everything, you will just make the network more complicated. Yeah, personally, I think the modeling of quantum bits, maybe you don't do it at the neural network level better, because it will add more complications here. Imagine everything is a softmax. Okay, I mean, that may be actually okay. Think about it, actually, Transformers has a lot of softmax. Every layer is a softmax. Yeah, who knows? Maybe the quantum modeling is very similar to a transformer, okay, for all you know. Yeah. Okay, any questions on this? Because actually this is, I think, the highlight of how they learn the logic gates using this backpropagation, and then during inference time, they just choose the gate that has the highest probability based on softmax. Okay, all right, let's move on. So as I said earlier, this is how they initialize. They do random initializations, okay? And then basically they use the Adam. So this is, if let's say they use a neural network, then they use the normal distribution for the weights. Basically, if they use the normal neuron, okay, but if they use the logic gate, then it's a random initialized connection. So there's two different things that they did, because they compare the neural network performance. Okay, for both of them, they use Adam, and they use 0.01 learning rate. They say Adam is used because Adam kind of remembers the last few gradient updates and helps to converge faster. I actually quite agree because Adam has been quite useful for me as well. So yeah. Next, the logic gate selection. As what I said earlier, the inference time, each of the basically based on the categorical probability, you will select the logic gate with the highest probability. Okay, so that's more or less it. Okay, so this is something new, right? Because when we want to do classification, we kind of want to do some form of like maybe softmax at the end in order to do the, so you can just, you want to use some form of cross entropy loss. So you kind of need to sum up the like outputs into certain classes. And basically what they do is, if let's say you have n output neurons and you have k classes, so what is very convenient is like you can treat this output neurons as like different students in the class, and then you group them into project groups, and then maybe each project group come up with an aggregated sum. So n divided by k students will be in one group. And then what you do is you then, okay, look at this equation here. Each group will have a certain like output, and then you scale it by a certain value and then add an offset. Yeah, so this is actually quite arbitrary, but they tune this on a hyperparameter. I think because when we do classification, you actually pass this through another softmax layer. So through the softmax, actually, it kind of regulates this tau and beta also. So you actually maybe don't need the tau and beta. This tau and beta was used, I believe, mainly for the regression problems. So I actually don't really agree with their regression approach. But at least for classification, because you pass it through a softmax at the end to do cross entropy loss, to do the backpropagation. So this will then train the neurons. Using this softmax, you can then backpropagate to each of the different the different logic gate neurons. Okay, and yeah, this is how they did the classification. The loss is trained using the softmax and then cross entropy loss. And the winner of the class will then be the class with the largest sum of the post softmax values. Or if you are doing like inference only, you can also count the number of ones at each class, or you just add up the output at each class. Okay, because if you do the relaxation of non-binary inputs, okay, you may not end up with 1. You might end up with like 0.4, 0.5, that kind. Yeah, so you just need to sum up the sum. Okay, maybe I can show you the diagram again. You just need to sum up. So at inference time, what you do is you just sum up, like in this group of students, there's 2 groups of students. You sum up the value, and you sum up the value and see who has the highest value. So over here, Giant Panda has the highest value. So Giant Panda is the winner for the classification. Yeah. So if you want to do a softmax, you can then put these values here. You can actually sum this up. Okay, and then you maybe, let's call this sum S1. So maybe S1 is 2. And then here S2 is 0. And then what we can do is then we can do a softmax distribution. So like we can do, for example, like e to the power of 2 divided by a temperature T. Okay, divided by e to the power of 2 divided by temperature T plus e to the power of 0 divided by temperature T. So you can see that this is like the softmax value of the first one. And for the second one, it will be e to the power of 0 over T divided by the rest. I mean, it's divided by this thing here. Yeah, so you can see that if we were to do like softmax classification, you will actually scale the output accordingly already. The output will all sum up to 1. So the additional terms that you see earlier, see in this slide, the additional terms here, this tau and this beta, I think these are not really necessary for classification, in my opinion. Yeah, I don't think these are necessary. Yeah, because if you can just use the softmax loss, you should be able to train the network already. Okay. So yeah, any questions on this, how they did the output? Okay, let's move on. So let's go on to results. So they did a few experiments. So the first one is on tabular data. So like the adult and like the breast cancer data set, they are actually doing binary prediction. Okay, I think adult is, I think also binary, yeah. Either 2 or 3 out. This one, I'm not too sure. This one might be 2 to 3 classes. But the breast cancer data set is either benign or malignant. So this is 2 classes. So again, the parameters that they take in, they are actually stuff like for example, breast cancer is like the size of the tumor and stuff like that. So these are like measurements in continuous values, and also can be some kind of different, like it can also be categorical, like male, female, that kind of thing. Yeah. So this basically has been mapped into like continuous values and then passed through different networks. So they did a few. So you can see like decision tree, logistic regression neural network, which is like MLP, and this is the diff logic net. Yeah, I'd just like to highlight that actually the accuracy that they obtain is comparable to the other networks. Okay. And even with a smaller number of parameters compared to like the neural network, they can actually achieve similar accuracy. The difference is this inference time here. So it can actually do the calculation in a very, very fast time. So this work is actually meant for edge devices because of this. Same thing for like the breast cancer data set. The accuracy is over here the highest. Okay, this one I'm not too sure whether it's cherry pick or what, but yeah, the parameters over here. Okay, this is the question I have. Like, how did they choose the parameters? Because like you see over here, this is 3 times, like almost 3 times here. But then when they compare this to this one is like times 0.6 or 0.7. Like, how come the parameters differ so much? Yeah, so this one I'm not too sure how they actually chose this. It looks kind of cherry picked to me. But the key fact that is undeniable is that the inference time is very, very fast. Okay, so this shows that the diff logic kind of architecture can be quite useful for edge devices. And it comes up with even better accuracy than the rest. Interesting, right? Yeah. Honestly, this kind of looks a little low for the rest also. Because I've done the breast cancer data set before. I think you should be able to get 90% over accuracy. So I'm not too sure how come all these are so low. Yeah. Yeah. So he says maybe regression needs more parameters because logic gates are inherently binary. Yeah, over here it's not a regression problem, this is a classification problem. Yeah, you either classify into like breast cancer is malignant or benign kind of thing. So this doesn't have the problem that regression faces. Yeah, so yeah, I didn't display their regression results because I just want to focus on classification. Yeah, I find the way that they did regression is a little arbitrary because you kind of need to like define your own tau and beta. These are not learnable. It's kind of you are trying to define your own regression output yourself. So I decided not to focus on this. But I think the classification is good. So I talk more about classification. All right, so we go to next one is binarized MNIST, where we try to predict the digits 0 to 4 as one class, and then the digits 5 to 9 as another class. You can see that the neural network performs pretty well. All right, but the leaf logic net can actually match the performance at a much lower rate of parameters compared to a neural network, which is pretty interesting. Okay, so this one, I believe the param is because when you do MLP, you have this different neurons here. So if they actually use like I think 1024 neurons. So if you do like your weights, right? Let's say four weights already. Your number of parameters here, if you count all the weights from all the neurons, it's actually like 4 times 4, like n by n. So it's actually exponential scaling because of the number of weights here. So the parameters here, all right, is because a neural network is fully connected. So like a fully connected neural network, you need like n squared weights plus n bias. Yeah. So it actually scales exponentially for neural network. Okay, whereas for like the DiffNet, they only have a maximum of 2 connections per input. So that's why the parameters are so low. Right. So it's actually not that fair a comparison. I mean, if I do like a hard fix to the neurons to make them only input 2, okay, maybe the neural network will perform better. Yeah. So there's some sparse neural networks as well that that they have done some experiments, but they don't have the full data, so I didn't show here. Yeah, if you're interested in that, you can look at the paper. Yeah, so these parameters, let's not look too much at it, okay, because of the way the experiments are done is kind of not apples to apples over here. But we look at the inference time here, you see, wow, this is like microsecond, nanoseconds, you know, compared to like milliseconds for neural network. It's like order of magnitude smaller, like 1,000 times smaller, I think, or 10 times smaller. You have to convert milliseconds to like microseconds. I think it's about 1,000 times smaller. Yeah. So it's actually quite fast. So if we just look at the inference time, the inference time is very, very fast for similar accuracy, and that's wonderful. Yeah, of course, the training time is about 3 to 4 times longer, all right? So yeah, there's some drawbacks to this because of the categorical probability kind of method of training. Okay, lastly, we look at CIFAR. CIFAR, again, you can see that the inference time is very, very low compared to like neural networks. And then if you use like student-teacher like learning or this, actually is also very, very fast compared to those, because it's also kind of neural networks. Okay, the accuracy, however, is not as high as like this kind of fully connected baselines kind of accuracy. Okay, mainly because if you look at the experiments they did, in order to make the diff logic network not have too many input parameters, they actually changed the color channels to a resolution of only 4. Okay, compared to a resolution of 256, which is the usual pixel resolution. So with a resolution of 4, you only have like 4 different thresholds for each image pixel, for each color pixel. So the neural network didn't do too well for this. So there's some information loss here. Okay, so if you just look at this color resolution here, it actually performs better than that kind of neural network. Okay, but the reason why they did not show their experiments here is because if you want to increase the channel resolution to 256, you kind of need a larger differentiable logic network in order to encompass the larger kind of inputs. So it scales exponentially in the number of inputs for the diff logic networks. So that's a problem, all right? That's a problem for larger models, because if you have even more input streams, you can't possibly just like increase your parameters exponentially, right? You look over here, the number of parameters is increasing so much, like in terms of like millions already. Okay, although it's like still smaller than this and smaller than this. Okay, if we were to do in this kind of like resolution 256, and you do the diff logic net, I'm very sure the diff logic net here may actually be larger than this, because of the way you need to like, I mean, if you do n choose 2, let's say you have n inputs, and then you want to connect everything fully, you need n choose 2 connections. Okay, if you look at this equation here, it's actually n factorial divided by 2. Okay, actually, I don't need to do everything because I know the answer already. So this actually, n times n minus 1 divided by 2. So this actually scales in the order magnitude of n squared. So this is O n squared. Big O n squared. Yeah, so this actually scales exponentially in the order of like of your inputs. So from 4 to 256, imagine the scale here. This one, the diff logic net will be much larger than 31.6 million. Okay, that's why they didn't do this. So this is a drawback of this method. Okay, but based on the accuracy of a like similar kind of input resolution of 4, it performs pretty well at a faster speed. So you can see there's some benefits of this method. It just takes 3 to 4 times longer to train, but the inference time is very fast. So there's some benefit to this. Okay, so let's take a look at the number of gates here. So you can see, if we look at like the data set here, number of like logic gates per layer for the adult is like 256, breast cancer is 128. Compared to neural networks, you just need 8 neurons and 32 neurons. And then you can see the apparent like CIFAR 10, you just need 1024 like normal neural network neurons. But for logic gates, you need up to like 1 million kind of logic gates. So you can see that it's it's not very sustainable if you have like a very large kind of input right now, okay, with the current kind of logic gates. So these are some of the limitations the authors highlighted. So about 3 to 4 times the training costs. And that's not a problem if you have unlimited time for your training, right? And this is actually due to this differentiable categorical distribution that kind of makes the training unstable. Okay, they didn't mention that the training was unstable in the paper. This is based on my assessment of the network. I believe it will be unstable because if suddenly change the logic gate, you change the function drastically, definitely unstable. Okay, so one way to actually make this better is not to change the logic gate at all, but to have some volume control, like what I talked about earlier. Okay. Next, we don't have like the benefit of ConvNet. Okay, but then again, the experiment didn't use ConvNet at all. They just use MLP. So, I mean, still okay for this. But if you want to scale it up to CNNs, you kind of need to have the same set of like logic gates for each of them, each of the like patches. So yeah, we need to think of like how to backpropagate all this because you cannot change the weights at all. The only thing you can change is the like logic gate. But if you use the method that I talked about earlier, like you do the volume control, you may be able to do this like using convolution and change the volume control across all patches. Yeah, so this may be possible. Like residual connection should be possible to model also, because you can actually backpropagate through this network. So you should be able to backpropagate through a REST connection as well. So I think these are small limitations. This can definitely be modeled. The key limitation is this one. Like, how do we stop this exponential growth of logic gates? Okay, so later we can talk about this. All right, so this is the last limitation, exponential scaling of number of logic gates. Okay, so these are some thoughts that I have before we move to the discussion. Okay, just give me about 5 to 10 minutes before we do the discussion. So what are some of the benefits of this network, in my opinion, is that no gradient vanishing and exploding. You realize you don't have to regularize this network at all. And that's because the output is kept to 1. And I quite like the idea of that. So while I may not agree with using logic gates are mainly for edge devices, but for the point of normal neural networks, I think we can still learn something from this, in the sense that maybe we could bring back some form of activation function that caps the output, and then we kind of scale the output using other means, okay, in order to avoid this gradient vanishing or exploding problem. Right? I quite like this a lot. And when I saw this poster, I was like, yes, we need something like that in current neural networks. Yeah, because I kind of think the ReLU function is very unstable. Like you can explode in terms of like your gradient. When you backpropagate a ReLU, the gradient is 1. Yeah, you actually basically, because this is the x, y equals to x function. So if you backpropagate, differentiate with respect to x, the gradient is 1. And that is basically passing through the entire gradient from the output all the way to the input. Yeah. And then if you sum up all these gradients together, you definitely have some form of exploding gradient. Okay, if the original like gradient is greater than 1, you have exploding gradients, because like 1 point, like maybe 1.4 to the power of like 1.4 to the power of 10, you know, you actually get a very large number. But if let's say your original gradient is like maybe 0.7 to the power of 10, you actually get a very low number. So these are inherent issues using the ReLU activation function. And I quite like the idea, if you actually cap your output to 1, you don't have this kind of problems. All right, the drawback, as what they said, exponential number of gates. All right, and also a lot of this compared to the normal neurons. These are actually quite bad things, because you cannot model something bigger. All right. So I was thinking maybe we could go another approach other than just modeling logic gates itself. We could just constrain the outputs by use a more expressive architecture to do a kind of similar idea that the paper has. All right. So these are some of the reasons why I say current neural networks are not exactly that great. We actually have to scale the input to 0 mean unit variance, like ImageNet pixels. Right? In order for ImageNet to train well, you need to do this kind of scaling, which highlights that neural networks are very sensitive to this kind of gradients. We need to do batch norm, layer norm. So like transformers, they initially started with batch norm, then they shifted over to layer norm. So batch norm basically have a 0 mean unit variance across all batches. So you can see the N is the batch. So this dark blue means the norm, the zero mean unit variance is across the batch. This is the batch. And then layer norm is across the layer of the network. So you can see that this is the channels of the, like, for example, CNN. Across all your channels, you actually have the zero mean unit variance. So these two norms are there because of the problem of this exploding gradients and vanishing gradients. So you need to kind of normalize them. So this is a problem that the neural networks face, but biological neurons don't have this kind of problems because we don't have this exploding outputs. Okay, same thing for RNNs. You have forget gate, input gate, output gate, specifically meant to counter this kind of exploding and vanishing gradients. All right. In fact, actually, I can add one more tool here. Actually, softmax actually helps to also regulates the gradients. Yeah, so I quite like softmax. So I think this is also a way that we can help to regulate it, because softmax, the outputs are constrained from 0 to 1 also. Okay, so yeah, this is just some idea, like what people used to do is they use a sigmoid function to constrain the output to 0 to 1. Or if you want to model excitatory and inhibitory neurons, you can use a 10H because 1 is excitatory and -1 is inhibitory. But the problem with these traditional networks is that the gradient saturates quite easily. Like, it's very easy to end up in this place and this place. Okay, and you will get 0 gradient here. Yeah, so how then can we solve this saturated gradients? And what I offer, like the solution that I was thinking of, is gated neurons, like use like GALU or something like that. Yeah, or in this case, like, because if you use like gated stuff, you actually don't have the problem of this saturation that easily because you control your volume. So this is still some thoughts that I have. Okay, still quite interested to like try to model as closely as possible to this kind. Which also might mean that we need to factor in some form of timing, spike timing inside the neural network as well. So actually there's this branch called spiking neural networks. But I think the papers on this are a little too complicated because like you need to model the time domain as well. I still more of a fan that you abstract out this time domain into like into a certain value. Yeah, so still thinking about it. Yeah. I think the spiking neural networks is interesting because you can do like Hebbian learning there, like neurons that fire at like the first neuron fire, the second neuron fire, you can strengthen the connection of the second neuron if the timing is within like a theta rhythm. Yeah, so there's some connection to neuroscience here. Yeah, so this part here, still reading on it. Yeah, I think the current neural networks are not very closely related to neurons, but they work. So that's why everyone's using it. But maybe there could be some benefits in looking at all this kind of alternatives. Okay, and lastly, one thing I was thinking about quite recently is graph neural networks, because like you can model neurons more than just in a layer. You can model them in like different clusters, and then this neuron can like transfer information to another neuron in the next time zone, and you can do that for every single neuron. So this is known as message passing. You can actually pass messages from one neuron to another neuron, and all of them can do so simultaneously in a graph neural network. So maybe if you model like a graph neural network, you can actually model the neurons better. Yeah, maybe it can do more functions, but the downside is that it takes a lot more compute power. Yeah, so this is another way of approaching like how to mimic biological neurons more closely. Yeah, so some thoughts that I haven't really consolidated fully yet. But yeah, let's do our discussion now on the paper. So yeah, y'all feel free to chip in as well. We start with the first question. Like, why do you think the authors only restrict to 2 inputs per logic gate? Why not increase the number of inputs? Okay, so maybe I'll answer first. I think it's because it's very hard to compute the equation for like more than 3. Like, they want to model all possibilities, right? So if you do 3 inputs, you have 3 to the power of 4 possibilities, which is like 81. So you need 81 logic gates. So this is why I think they only restricted to 2. Yeah, you have any opinions on this?
Yeah, it's definitely to do with scalability. You were doing it previously on the 16, right? The 2 to the power of 4, The reason is because if you add more, now it's no longer binary. You need to count for all the respective A, B, and C combination. So like what you drew, it's going to be 3 to the power 4. If, let's say it's, and this 4 is not even fixed. It depends on your final layer.
True, true. Yeah. So actually this one, yeah, I mean, if we look over here, or maybe actually it's not, maybe it's not 3 to the power 4, because like you have 3, actually it's 3 factor, sorry, I think it's not 3 to the power 4. So you need,
it's the number of actual inputs to your function. So
right,
let's say
0, 0, 0, 0, 0, 1. Yeah, so it's actually like the number of permutations of all this until 1, 1, 1. So that is actually 2 to the power 3. So 2 to the power 3, and then you also have an output that you need for all this, right? So it actually is 2 to the power of 2 to the power 3, which is 2 to the power of 8, 256. Yeah, so 256 gates, because like here is either 0 or 1 for each output. Yeah, so actually it scales exponentially.
oh no, it's not base 2, by the way. You have 3 inputs.
Yeah, so you see over here, this top here, these are the inputs. So input 1 is 0, input 2 is 0, input 3 is 0. So there's a total of 2 to the power of 3 different kind of combinations of the input. And then each of these combination, you have like a potential output that you need to map to. And the output is either 0 or 1.
Computational issue aside, what's the point?
Sorry, say again?
Computational issue aside, what's the point?
Oh, no, if you have more inputs, right, you can actually let the function learn better. Like, because right now your random connections actually determine whether it learns or not. If you have,
What's your logic gate here? If it's an AND gate, you can just stack multiple AND gate, right?
correct.
Okay,
It's the
how
same
about
for
this?
all,
Let's
it's
not
same
think
for
about
all these.
AND gate. Think about this. So you're asking what's the point if we want to increase to n number of inputs, right?
Yeah.
You can think of the inputs as you're trying to find the relation between all these inputs. So let's say you only have 2 pairs of inputs. So 0 or A and B. You're actually trying to find what's the relation between A and B. So if let's say I can increase this to number of n, so let's say A all the way I can count. So all the way to, let's say, G. Now I can draw understanding on how A is related to A, B, C, all the way to G, instead of just limited to A to B.
You can compose it with multiple binary input gates, right?
yeah, actually you can compose 3 gate with a double 2 gate. Yeah, I think
So
that
that's why I'm asking what's the point, since you already can compose it.
true.
I guess maybe we can talk about if it's a direct relation, because if you compose it, it's still a process, right? So
Basically,
you can kind of
you trade off the number of gates with the number of inputs, right?
Yeah, actually, why I was thinking about this is because like there's actually an exponential scaling based on like a 2 input gate. Imagine if I have like a total of like 100 inputs, all right, and then you have to feed all these 100 input into your 2 input gate. You have 100 choose 2 possibilities. And if we can like do some form of like fully connected or like connect a lot more, you can actually not scale up exponentially so fast. So I was thinking of this, but if you were to do something like this, your logic gate cannot be the normal logic gate anymore. It has to be some logic gate that is something like a graph neural network. You can have to do those kind of things that are commutative, like for example, n, or you can scale up to arbitrary numbers. Yeah, so there's some benefit to increasing the number of inputs, but then you probably cannot model all possible input-output relations anymore. But you know, De Morgan's law, right? I think you can just use NAND or OR gates. And if we just use only these 2 gates, maybe we can actually scale the number of inputs more, like to 3.
No. The trade-off of De Morgan's law is you actually have to expand the number of gates you require to model a logic. So if you just use N or O, right, you're going to get a larger network instead with more parameters.
That's true, but you don't naively brute force all the possible combination, right? Because you have an optimization you have a way to learn it, so you don't naively just go through all the combinations, right?
I'm also quite skeptical on the learning. The idea itself, I guess I can buy the quicker inference, but initially when Jomi was presenting it, I was trying to think of a link, like for example, ensemble learning. But then I realized
They
most
didn't
of
do
all
ensemble,
the
they-
inputs aren't actually going through the same network anyway, so it's not exactly ensembles, and it's very concerning in that way. Like if you take a different set of inputs from a different class, like no longer a panda, and you feed it in, there's a high chance that the subnet that is used to classify panda was you say, oh yeah, it's a panda, when it's not.
No, but actually you can learn the logic gate, right? So you can actually, through multiple iterations of epochs, you can actually learn the right set of logic gates to classify any kind of class. You can treat the logic gate like a weight in the neural network.
So probably here maybe is trading off the number of inputs to the training time, since you already mentioned the training time also quite long.
Yeah, it's actually very long. Like for MNIST, you guess how long they took for MNIST?
I don't know.
I don't like the way they use training time, by the way. In order to figure out the right gate, they're not factoring this under training time, right? They just
They
actually
are. Yeah, so the training time for MNIST, I believe, is 1 hour 40 minutes to train to the accuracy on MNIST. But the neural network just needs about 10 minutes, 5 to 10 minutes.
So
Yeah,
to find they say the better fit of logic gates, it's 1 hour.
yeah, 1 hour plus. I can pull out the paper lah. I mean, then we can look at the train, but you can
Is
just take
this,
my word for it.
did they submit this to any of the conference?
This is NeurIPS.
NeurIPS.
Yeah, it's an accepted paper in NeurIPS. It's actually quite cool because I was quite excited by this paper, but not because I want to
The
replicate
accuracy
paper.
really cui leh.
Oh, but you can't treat it as other people because it's trying to come up with a novel, like
Yeah,
entirely
correct.
novel way to.
Yeah, I do understand that. It's just that usually because if you read enough paper, usually the benchmark of like if you see a certain data set, right, you already expect a certain
Yeah, actually MNIST
accuracy.
can go up to 99%, and some of theirs is binarized MNIST, so it's even easier.
Yeah, I was expecting something like okay, maybe not 90%, but maybe like in the sub 80s. But then you show me like it's 60%.
Oh, you're talking about Cypher, is it?
Yeah.
Yeah, Cypher actually 60% for MLP is quite impressive.
Yeah,
Just
C5 is quite hard.
yeah, Cypher is quite
sometimes.
hard a data set.
Yeah.
Yeah,
Especially for MLP. Yeah, MLP is hard.
usually for CNNs you expect about 80%, but MLP
I would never trust a paper that link MLP except maybe for this subcategory, because if you want to do MLP, right, you're automatically not assuming your model will generalize anymore outside of the training bounds. Automatically, you assume already. That's your assumption.
yeah, actually CNNs are good for images because of the shared weights. So if you don't use the shared weights, you will take longer to learn, much longer to learn. Yeah, so MLPs don't do as well on images because of the non-shared weights.
Not only that, as we were talking about like the spatial dependencies in the picture in image data sets, you're not exploiting that with MLP. In this case also, I don't see any bias. It looks more like a hashing function to me, a logic gate hashing function.
Yeah, the logic gate actually feels a lot like a fixed function, right? That you just map the inputs to outputs.
Yeah. Did they try any okay, this is quite new, so they probably haven't like adversarial image and you see the adversarial effect on it.
Yeah,
Like
no,
a panda that
I don't think it's done yet. But you can do it as a subsequent paper, then you can publish again.
no, probably not, because they are doing thresholding, right? So yeah, probably it's not going to be that well, not that robust to adversarial effects.
Yeah, no, I mean, I'm just thinking in terms of the author's perspective about like how to scale. So, I mean, back to this question, like you can increase the inputs, but then that will come at a limited expressibility. Yeah, so it was, but either way, I think we definitely need to limit. So it's actually related to this question. I think we just need 2 or 3 gates. We don't need 16 gates. Yeah, maybe we just need the no gate. Yeah, the no input, no output gate. Yeah, because this is plus 2 other gates. I think that will be enough already. Of course, you need a deeper depth, but that should be fine. If you can link all the inputs together, and then this is a very radical idea, you can actually put different. Okay, I know they didn't want to do like weights, but if you can do a learnable weight, you can actually, the weight is basically a volume control here. You can actually tune like how much of this input should be looked into, like based on the weight. So in some sense, it can shut off certain connections. Yeah, so you can start off fully connected, and then through learnable weights, you shut off certain connections. Because like you can just times 0 to this input, and then it will basically be a shut off the input stream. Yeah, so you can then do like you can do fully connected, and then let the neural network learn which weights are important and which weights are not, using like a tunable volume control thing. Yeah, so I mean, this is just an idea that I have. Yeah, because if not, it's very hard to scale to very, very deep layers, if you just use the logic gate with unlearnable weights. Because you cannot learn anything to control the input, and you cannot learn anything to control the output. The only thing you can do is to change the gate. That is a very slow learning. Yeah. So my suggestion to the authors, if they are watching this video next time, maybe they can consider like Galoo style volume control, the input and output.
Then do you also need things like a backprop to learn the weights?
Yeah. Of course, you use backprop to learn the volume control.
So you are trying to find the sweet spot between this logic gate kind of line of thought and the normal way of doing it.
Correct. So actually, my own take is that logic networks cannot model a lot of things. So I still think neurons are still better. Yeah, I only decided to like talk about this paper, not because I support logic gates, but because I feel like the way of constraining the output is actually this last question here. I think this is a very nice way of doing it. Like, I think we need to look at more neural network architectures that restrict the output, because gradient exploding and gradient vanishing is a huge problem. Yeah, so this is actually my key inspiration for choosing the paper, not because I'm interested to make it run on edge devices. So it depends on what your perspective is. If your perspective is to make it run on edge devices, then you cannot do whatever tunable volume control I'm talking about, because that doesn't exist right now on edge devices. Yeah. Oh, wait, actually I'm wrong. You can do the learnable volume control on the software. After you learn which are the important like connections, then you can implement them on the logic gate. So
I kind of doubt that this will be popular or well received in edge devices even, because the main premise of importing this to edge device is that you still need to have a certain performance. And
it's performing pretty well, right? I mean, look at the tables.
Yeah. Depends on how you say well.
Yeah.
And another thing is that usually when people train the network, right, they're training backend on some very, very high performer like GPU, like 16 cores, like then multi-parallels. Because at the end of the day, all you're trying to get is the weights for the set of a network. So it's actually the size of the network that should be optimized for each devices rather than the actual inference. Unless it's like a very specific scenario, like you want to have a high performance camera to a event capture camera, then maybe you can try this. But then again, the accuracy is very subpar at the current state. Maybe the author proves me wrong, and then they get a subsequent paper and it improves the accuracy. But now, yeah, I just don't like it.
Yeah, I think definitely the accuracy can be improved with a wider network. Or if you can come up with ways to do convolutions on image, then the accuracy will be better. Like you can do shared logic gates. Like instead of doing shared weights,
you don't have to
shared
do
logic.
convolution. I think the idea we're talking about here, it's the closest that you can do for that resembles convolution for logic gate. You just increase the inputs, because that mirrors the actual relation in, not exactly in convolution, but you are trying to pair them up, right, to get the result here.
Sorry, just one clarification. So I think my current takeaway, like the one of the strength of this method is to like you mentioned it kind of solve the problem of vanishing or exploding gradient, right? But then you still need, in order to learn some more complicated function, you still need the very many number of logic gates, right?
Yeah, that's
So
the thing that I don't agree with.
So how does it fit into edge devices scenario? I don't understand.
Oh, because edge devices, the inference time is important.
He's purely doing it on the nanosecond inference time.
Yeah,
Which-
yeah. So if you,
Oh,
yep. So
I
so
see.
if you already know your input output structure in terms of logic gates, you can run very fast. You already, so basically this network, when you implement on edge device, you cannot learn anymore.
I think edge device, some of the concerns. One is the inference time, because it's kind of related to power consumption, right? But then you want to learn it, you also need consume more power because you train for a longer time. And another very important factor is the size of your model. You must make sure it can be fit into your edge
Oh
devices
yeah,
memory, right?
definitely. Yeah.
Yeah.
So
yeah.
one strength about this method is that you don't need GPUs at all. So it can all run, I believe, on an FPGA array because it's all logic gates.
But so does FPGA inherently has more memory, or
It's just a way of connecting logic gates together. Yeah,
so can it fit a moderate large size of this kind of model?
You can always inbuild more memory into your FPGA.
you can always
board.
you can always
Yeah.
connect more FPGAs together. But anyway, the power consumption is very low for this kind of model.
I see.
Yeah. So there's some benefit to this. It's just that I feel like it doesn't scale very well. And in order to do it to the next level, I believe one way to do it is to not model all functions. You increase the number of inputs here. Okay, so we only model like a certain number of gates and we restrict the expressibility. But then again, during training time, you need to have some like volume control knobs here that you learn using like sigmoid function. Like you learn some form of volume control switch to then see whether or not should you tune up or tune down certain weights. And then like when you implement it on the edge device in the end, you can just do a like maybe thresholding. Like if it's above 0.5, then you on it, below 0.5, you off it. Yeah, so you can possibly do some form of like learnable connections, because I find that the arbitrary connections right now is very, very bad. It doesn't scale very well. Like n choose 2 doesn't scale well at all. It's best to give it fully connected and let the network learn by itself. And we should keep the logic gates fixed because it takes a very long time if you suddenly change the logic gate. So this is something that I don't agree with the paper. I think the logic gate should be fixed. But what you should do is you should just change the connections of the logic gates.
John, I
Yeah,
have
like-
a intuition that they tried fix logic gates initially, and it did really badly. That's why they did the subsequent follow-up.
Yeah, it's badly because you have n choose 2 amount of gates. Imagine you not just need n choose 2 now, you need n choose 2 times 16 gates. So if you miss out the right gates, right, it's actually very, very bad. You may not be able to learn that well.
Also,
But
how do you
yeah.
how do you okay you shall
Oh, yeah,
continue
yeah. But if you have learnable connections here, you don't need that many gates. You just need like a few gates, and then you can like, if you can do a fully connected, like these are your inputs, you can do a fully connected all the way into like a logic gate. You don't have to have so many gates. You can just have one gate of each, and then instead of learning the gate, you are actually learning the connections. You are actually learning which connections to take out and which connections to put in. So you just need to have like at each layer, in the ideal case, at each layer you just need to have like maybe 16 gates or like the gates that can actually like learn these connections. Then you don't need to have so many gates already. This is my thoughts. Yeah, this is my own thoughts. Yeah.
So can you actually have learnable gates on FPGA? I'm not very familiar with that.
No, you cannot.
Right.
Once
Then
you
if you
get
want
the
to,
N on all is fixed, because you need to
Yeah.
you need to what do they call it again?
You need to
The
program
solder,
it.
yeah, you need to solder those logic gates onto the board itself.
right.
Wait,
So
no. FPGA can pre-program. You don't solder it.
oh, so can be learnable.
You can use. No, actually, let me think about it. I know there's a kind of FPGA that you actually like destroy the connections if you don't want to use it. But there's also another kind that you can program it. Yeah. So
Okay.
I'm a little rusty here. I need to go and take a look at FPGAs again. But I believe there are some that is reprogrammable.
I see.
Yeah. But Dylan, you're talking about those kind that is one use and you cannot change one.
Buddy,
also-
I have it's like how many years ago? So I can't remember.
Yeah, we are both from electrical engineering. So I studied this a long time ago. So yeah. So yeah, let's talk about the last question before we end. Okay, so like, should the logic gates be pseudo randomly initialized or fixed set of connections? So this is similar to what I was talking about. Like, I think it should be fully connected for greater expressibility. And then after that, you prune it using some form of volume control. That will be better. Yeah, if not, you need to have too many logic gates per layer. Yeah, it's actually quite infeasible for scaling. Yeah. You
What
want
do
to
you mean
add?
by pseudo random?
Oh, it's by a random seed.
Oh, okay.
Yeah, you can just ignore the word pseudo. You can just treat it as randomly initialized.
He added pseudo because there is no true
Yeah, that's
randomness in generating.
correct. You all need like a seed for random number generators.
Yeah, I think okay. The bad thing about having fully connected again is that it's gonna sacrifice the training time for maybe slightly better performance for getting the better local minima.
Oh, actually, I think the training time will be much faster if we don't.
Really?
If we keep the
I
logic.
thought you said once you change one gate, the thing actually fluctuates really quickly.
Oh, correct. So I'm proposing we keep the logic gates fixed, but the connections are the one that we change. Yeah, it's something like in biological systems, your excitatory neuron and your inhibitory neuron don't just suddenly change. They remain excitatory neurons all the way and inhibitory neurons all the way. It's just what are the connection strengths that's the thing that changes. So I think this kind of approach would be better than, you suddenly use a categorical distribution and change your logic gate. I don't agree with this approach at all. Yeah. I mean,
I seriously think they tried the first one, which is to have fixed one. No, this is the intuition I get, that they tried it first, because usually when you go into this paper, right, you will try plan A, and then if plan A doesn't work, you try plan B.
that's why the relaxations are all try to make it work better than
exactly like when you're presenting. So it's probably they tried the fixed gate. It didn't perform very well.
Maybe.
And then they have to input this relaxation like you were talking about.
Yeah. Maybe we could get the authors to tell us. Yeah, but anyway, I was thinking something like this would be nice also, if we could do some GNNs. And then over here, instead of ReLU, we use like sigmoid or gated kind of networks. Yeah, because I do think like graph neural networks are very expressive. Okay, but this is a different direction here. Yeah, this is like more like trying to model like neuron connections using graphs. Over here, we are trying to do edge devices. So this is a different focus. This focus here is more like prevent neuron vanishing and exploding. Yeah, so this is kind of different. Yeah.
Speaking of different direction, right? I still stand by what I said just now. I think content ML community will be very interested to look into this direction.
Which direction? You mean this logic gates, is it?
Yeah, gate level, because what they do, like they don't have high level algorithm. Everything they do is programmed on gate level. So this paradigm is very natural to them.
Yeah. So
Yeah.
that's why there's a developing community on this on this logic gate networks.
Actually, I just shared it with my friend who is doing quantum. Yeah.
Yeah, it's a very interesting paper. In fact, this poster is the most remembered poster by me in the entire NeurIPS conference because they use black color as their base. All posters are using white. They really just spam the ink. They printed black, and then the text are in white. So that's why you want to stand out, you need to do something like that. Yeah, that stood out, and I thought the idea was interesting. Just that I think I'm not too interested to like model logic gates. I'm more interested to see like how we can use this to better model biological neurons. At least that's for me. But for your friends in quantum, maybe they'll be interested in the logic gates itself.
Yeah, I think so.
Okay, if not, any other things you want to talk about the paper before we end today's session? Okay, yeah, anyway, thanks for the discussion. I think it's very interesting. I wish the authors for this paper all the best in like furthering their work. It's a very interesting direction. And yeah, hopefully one day we'll have like better networks related to this. At least for my aim, I aim to have better networks that don't need to do any normalization at all. Yeah, so that'll be the like future aim as well. All right, thanks everyone.